Applications of vectors. Okay, let's pull it all together. And our objective here, let's solve application problems that involve force, velocity, and displacement. All right, we know a lot of things at this point, and they're all going to come into play here in one way or another. We know that any vector is made up of its components, its x component and its y component. So we can replace a vector with the sum of its components, and we have the same thing. We know that the reference angle is the inverse tangent of the absolute value of the y component divided by the x component, the vertical divided by the horizontal. Now, in this case, in a number of cases in real life applications, we're dealing with positive things in real life, not a lot of negative in real life. So we'll probably see that we don't need the absolute value signs here, but the absolute value signs can come into play as well. We know number 3, given a vector's magnitude is equal to the square root of its x component squared plus its y component squared. This comes from the Pythagorean Theorem. We know from trigonometry that the x component of a vector is equal to the magnitude of the vector times the cosine of the angle, standard position angle. The y component of the vector is equal to the magnitude of the vector times the sine of its standard position angle. And finally, we saw in our previous lesson, when we have 2 or more vectors that are not at right angles, they can still be added, and we use their components to do that. Okay, we're going to add the x components of all the vectors involved. We're going to add the y components of all the vectors involved, and that will give us the sums of those 2 things will give us the x and the y components of the resultant. Okay, I'm going to do 3 examples here. And slightly different. We're going to start with perpendicular situation, and then we'll get into a couple of other situations, including one involving equilibrium. So here's our first one. Hope I can get this all set up correctly. 2 hockey players strike the puck at the same time, hitting it with horizontal forces of 6.85 pounds and 4.5 pounds that are perpendicular to each other. That's key, of course. Find the resultant of these forces. As always, a picture makes a huge difference. Now, these 2 vectors, these 2 horizontal forces are coming at each other perpendicularly. So let's do our x and y axes here. And why not, if they're going to be perpendicular, why not take advantage of the origin and the x and y axis? And let's make this one, this is the vector. I'm going to call this vector, it doesn't matter, we'll call this vector A. And this is the one that has a force of 6.85 pounds. Okay. The other horizontal force is perpendicular to this one, so we'll go up on the y-axis. It's positive, so I'll go like this, and we'll call this one vector B. Again, they're perpendicular, and this one has a magnitude of 4.5 pounds. Okay, so that's important. They're hitting one another perpendicularly, so we have a 90-degree angle. What is their resultant? Well, these vectors are tail to tail, so we can draw a parallelogram, or in this case, the parallelogram is a rectangle, and we can connect the tails to the opposite sides to come up with the resultant vector, R. I'll label this R in this case. So what is that? So we're looking for the magnitude of vector R, and we're looking for the standard position angle to give us the direction. Okay, so what do we know? Well, we know the magnitude. So these vectors are perpendicular. Okay, they are at right angles. So we don't need to worry about this step here because they're already at right angles. So we can just look at it, and magnitude r is equal to the square root. Okay, in this case, it's going to be the magnitude of the x component squared plus the magnitude of the y component squared. R is equal to the square root of 6.85 squared, the magnitude of vector A, plus 4.5 squared, the magnitude of vector B. Pop it into a calculator, and I came up with 8.20 pounds. So that's going to be the magnitude, the size of the resulting force, 8.2 pounds. Okay, what is the direction of this force? Well, you can see it's going to be an acute angle. Just looking at it, I don't know, looks like because the x component is longer, it's probably an angle less than 45 degrees. Let's find out. So the direction, okay, we know that theta is equal to the inverse tangent. We know that theta ref, okay, again here, theta ref, but this is already in the first quadrant, so I'm going to ignore the ref part and just say theta, because I'm already in the first quadrant. The inverse tangent of the y component, which is 4.5, divided by the x component, which is 6.85, and I pop that into a calculator, and I came up with 33.3 degrees. So there you have it. Find the resultant of these forces. We just found it. The resultant force is 8.2 pounds at a direction of 33.3 degrees from this force, the way we've drawn it. Let's write that down. The resultant force, that's what we're looking for, is 8.2 pounds. That's the magnitude. It's 8.20 pounds at a direction of 33.3 degrees. And in my diagram, that is up from, so from the 6.85 pound force. There you are. It's coming from this vector, from that force, the way we've drawn it. So there you have it. There's a first example, a little real-life application. Let's move on to example number 2. Give me a moment. I'll turn my paper over, and I'll reset my notes here. As you might imagine, I got to do all these problems out and make sure I'm clear on stuff before I start videotaping. That takes a little bit of time. Okay, so example 2. A ship sails 32.5 miles east and then turns 41.25 degrees north of east. After sailing another 16.18 miles, where is it with reference to the starting point? Okay, let's draw a picture. I can't emphasize enough how important it is to have a picture of these things, so that you have a sense of what's going on. It really does make a difference. So x and y. Okay, so we're going to say the x direction is east, the y direction is north. Okay, we're on the rectangular coordinate plane again. Here's our ship, 32.5 miles east. Okay. And there we go, 32.5 miles east. I'll call this vector A, and its magnitude, is 32.5 miles. Its magnitude is 32.5 miles. Its direction is east. It then turned 41.25 degrees north of east. So it went like this. It turned it turned 41.25 degrees north of east, and it went for 16.18 miles. So here's vector B, and its magnitude, B, is equal to, again, the vector has the arrow over it. The magnitude of B is 16.18 miles. This is miles. Sorry, I forgot that. And that's where it ends up. So it went 32.5 miles east. It turned 41.25 degrees north of east, and then it sailed another 16.18 miles. Ends up here. Where is it in reference to the starting point? Well, here is the resultant vector right here. So where is that? What is this theta, and how long is this? What is this magnitude, and what is its standard position angle? Okay. Notice these vectors are not at right angles, so we're going to need to make our table. Okay, so make our table. Not a big deal. We got to find the components. So let's see here. Vector, magnitude, standard position angle. That's my first set of numbers. Okay, I've got vector A, vector B. I'll underline that. You should be getting pretty good at this by now. And vector R, the resultant. The magnitude of A is 32.5 miles. The standard position angle of A, well, A has a standard position angle of 0. It's along the x-axis. That's pretty nice, 0 degrees. That's going to come in handy because that's going to make it kind of easy to do some math in just a few moments with the x and y components. The B vector, however, has a magnitude of 16.18, and its standard position angle is 41.25 degrees. That's our first part. Okay, let's take a look at our x components. Well, let's look at our x. Let's look at A. A is a horizontal vector, so it only has an x component. There's no y component. It doesn't go up or down at all. It only has an x component. So our x component for A is simply 32.5 miles. If you want to do this times the cosine of 0, you'll get the same answer. Okay, because the cosine of 0 is 1. 32.5 times 1 is here. Okay. B, however, this is its x component. Excuse me. From this point to a dotted line here, that's B's x component. That's going to require our magnitude times the cosine of the standard position angle. And the math on that one says 12.16. Okay, and we know that our resultant x component, we can find this by adding up the x components, is going to be 32.5 plus 12.16. So the resultant x component is going to be 44.66 miles. So from here to here, from this point at the origin to this point straight down below here is going to be 44.6 miles. That's the x component of the resultant vector. Let's do the y components. Okay, well, here's my A vector. You'll notice there is no up or down. There is no y component. That one's easy. The y component of the A vector is 0. Okay, because it's a horizontal vector. There is no up or down component. It's only a horizontal component. So the up or down component is 0. Now B, of course, from here to here is its vertical component. So we can do the same. We got to come up with that number. That's going to be the magnitude times the sine of 41.25 degrees. Into a calculator that goes. And that's 10.67 miles. So from here to here, this vertical direction over here, it's the R, this vector's y component is 10.67 miles. Okay, so our resultant vector is equal to the 0 plus plus 10.67. That's pretty simple. The y component is obviously simply 10.67 miles. Okay, we've done the hard work. So now let's put what we know. Okay, let's put together what we know about, let me make sure my paper's decent here. Okay, so we know magnitude and direction. Magnitude. Okay, what is R's magnitude? Well, R's magnitude is the Pythagorean Theorem, which again is the x component squared plus the y component squared and the square root of the sum. Okay, the square root. This is the x component, so 44.66 squared. This is the y component is here, 10.67 squared. Into a calculator it goes, and the resultant vector's magnitude is 45.92 miles according to my calculator. Come up to here again, and you'll see from here to here, we calculated as 45.92 miles. Okay, 45. Now what is this? What is this angle? That's their standard position angle. Okay, let's find the direction. Okay, well the direction is theta is equal to, and again I'll go back to the diagram. You can see we're in real life, and so we're positive. So we can calculate the reference angle, but it's going to be the exact same thing as the true answer. So I don't need to worry about that reference angle because of where this is. We know that this angle is positive. So the inverse tangent of the y component divided by the x component is the inverse tangent. The y component is here, 10.67. The x component is here, 44.66. Once again, pop that into your calculator, and out comes, I hope, 13.44 degrees. So I look up here. Does this seem to make sense? Well, yeah. I mean, I knew it was kind of acute. It's not going very high. It goes a long way this way, then it kind of goes a little way up. That angle is certainly going to be less than 45. My drawing is not to scale by any stretch of the imagination, but we should have a smaller angle anyways. Okay, so so now we know the reference to the starting point. Let's make a note of that. Just a second, let me get my paper straightened out again. Okay, so the ship is 45.92 miles. Okay, that's its magnitude from the starting point. That's what we were asked. What is its reference to the starting point? Okay, we got to give its direction. Remember, a vector is magnitude and direction. In a direction, 13.44 degrees to the north of east. Okay, so we chose this to be east, and we went 13.44 degrees to the north of that, and that's what we have here. All right, let's get to one more problem, and I'm going to pull in a vocabulary word. And this might be the most difficult of the three problems. That's all right. We're gonna work right through it. No trouble at all. Okay, we're gonna pull in a word, the word equilibrium. Okay, equilibrium, as defined, is a state in which opposing forces are balanced. Okay, when something's in equilibrium, the forces on it are balanced. In other words, the net force, all the forces acting on it, all put together, is zero. Okay, so we're going to make use of that idea here. All the forces acting on an object that is in equilibrium, when we add them all up, we get zero. Okay, what does that mean in terms of vector language, if you will? Okay, in vector language, what this means is the condition of an object being in equilibrium is satisfied when the sum of the x components of the forces is 0 and the sum of the y component forces, the y components of the forces is also 0. So notice here, we got a number of zeros going on we have to put into play, okay? Because equilibrium means the sum of those forces is 0. So let's take a look at an example of this. Example 3, a 165-pound rock climber is climbing a vertical rock face suspended by a rope that is angled 60 degrees from the horizontal. Here's the rope, here's the horizontal, 60-degree angle is right here, okay? If T is the tension in the rope, so this is T, that's the tension in the rope, and F is the horizontal force with which the climber pushes away. So this is F, the force is pushing, the climber is pushing away from the rock face. Find the magnitude of these two forces, T and F. Now notice we also have a third force here. Okay, we have weight that's working on this climber. So I'm going to call this vector W, and its magnitude, this climber is 165 pounds. So here is the W is the magnitude of the weight vector. Now notice that weight as a vector, it's always to the center of the earth. Weight is always measured perpendicular to the, straight down is weight. Okay, now let us draw this with the climber's body. Let's draw this using our XY diagram. And let's also remember that we need to have the tails of all of our vectors. So here's X, here's Y. Okay, so weight, that's probably the simplest one to start with. The W vector is going straight down. Okay, and so here's the W vector. And the magnitude is 165 pounds. Okay, the tension vector is fairly straightforward. We do a 60-degree angle. And here's the tension vector right here. This is T. We do not know its magnitude. We're being asked to find it. Find the magnitude of T. We know the vector is up here. We know its direction. We don't know its magnitude. Now here's F, okay? Now, it's kind of hard to think about in terms of this climber is pushing away from the wall. How does the vector, how does this vector go? Where's the initial point? Where's the terminal point? But keeping in mind that we're going to have our initial point at the origin, this vector goes this way, pushing away from the wall. There's your vector. Or some people see this as the cliff pushing against the vector, the cliff's push against the vector's body, okay? So this is the horizontal force, and we know that's a vector, but again, we don't know its magnitude. Okay, so we're looking for that. Find the magnitude of the two forces, T and F. But here's the situation. Okay, we have our three vectors. Our climber's body is the center of this situation here because all three of these forces are working on the climber. The weight is pulling the climber down. The rope, the tension is pulling the climber this way, and the cliff face is pushing the climber this way. Okay, so we got some perpendicular in here, but we've got three of these, and they're not all perpendicular. So let's make our chart. Okay, vector. Magnitude. Whoops, if I can spell magnitude, that would be helpful. Let me push up a little bit here so we can see it. Okay, vector magnitude and standard position angle. Okay, we'll start here. We have vector, we'll do T first. Doesn't really matter. I'll do F second. And I'll do W third, and then of course we have a resultant vector from all of these forces. Okay, so we're still in the same place. We're doing the same thing a number of times now. The magnitude of t, we don't know. We're looking for it. It's just going to be t. It's an unknown. The magnitude of F, okay, the horizontal force. Again, we don't know it. Find the magnitude, so just put F. Those are our two unknowns. This is what we're looking for. We do know the magnitude of the climber. The climber's weight is 165 pounds. Okay, so we're going to look for the tension, the number of pounds in the tension, and we're going to look at the number of pounds of force, the horizontal force with the climber pushing away from the rock face. Standard position angle, we're looking over here. T is pretty simple. It's 60 degrees. Okay, F, well from here to F is 180 degrees. And from here to W is 270 degrees. Standard position angle. So far, we're in a good place. Okay, let's do our X components. Okay, the X component of the T vector is, remember, it's magnitude times the cosine of the standard position angle. So T cosine 60 degrees, and that's approximately, not approximately, the cosine of 60 degrees is 0.5. This answer is 0.5 T. And I know that's not a number, it's a multiplication problem. Just hold on a second, we're going to get there. But this is the X component of the T vector. It's 0.5 times the magnitude of the T vector. Okay, what is the X component of the force, the horizontal force vector? Well, it's the magnitude of the force vector times the standard position angle. F times the cosine of the standard position angle. The cosine of 180 is -1. This is negative F. Okay, what is the, let's do the weight, the X component of the weight vector. It is the magnitude, 165, times the cosine of its standard position angle, which is 270 degrees. And that turns out to be, well, the cosine of 270 is 0. 0 times 165 is 0. Okay, let's go ahead and add these up, because I want to show you something here. Okay, so the resultant vector is equal to the sum of the three of these vectors right here. Okay, that's the resultant vector. And we go back up to here and we notice, okay, the condition of an object being in equilibrium is satisfied when the sum of the X components is 0. Okay, so we want, get my paper straight, we want this to be 0. We want to add up these X components and get 0. That means they're in equilibrium. So this is 0.5, this is negative F, and this is 0. Okay, as a reminder, equilibrium means R sub X is 0. The sum of these is 0. So we come up with, so we have an equation here. 0.5, oops, I forgot the T. The T, you probably caught that on watching the video. This should be 0.5 T. I bet you wonder what I did with that T. 0.5 T minus F equals 0. Okay, so we have an equation here. We know this is true right here. Okay, we know that the sum of the X components must be 0, so R sub X is 0, and we have this equation right here we're going to make use of. Let's do the Y components now, and you'll see something similar happen. Components, if I can spell components. Okay, the Y component of the tension is the magnitude, T, times the sine of the standard position angle. And this comes out to be approximately 0.866 times T. the y component of the horizontal force of the climber pushing away is going to be F times the sine of 180 degrees. Well, the sine of 180 degrees is 0. 0 times F is 0. And the y component of the climber's weight is the magnitude 165 times the sine of the standard position angle 270 degrees. Well, the sine of 270 is -1. So this is going to be -165. Okay, so r sub y is t sub y plus f sub y plus w sub y. The y component of the resultant vector is equal to the sum of the y components of the three vectors. And so r sub y is equal to 0.866t plus 0 plus -165. Okay, now let's remember, equilibrium means, okay, that the sum of the x components and the sum of the y components, the sum of all those forces is 0. That means that r sub y equals 0. So we have 0.866t, didn't forget it this time, minus 165 equals 0. And this equation is the one we're going to play with right here. Okay, let me shift some stuff out of my way. Okay, so what do we end up with? We're looking at, as a reminder, we're looking to find what T is, what is the magnitude of the tension vector, and what is the magnitude of the horizontal force vector. And they're embedded in these two equations. So we have two equations, 1, 2, in two unknowns. And this takes us back to a little bit of Algebra 2. Okay, and I'm going to write them like this, which you've probably seen. I'm going to write them as equation 1, 0.5t minus f equals 0. Equation 2, 0.866t minus 165 equals 0. Those are my two equations in two unknowns. If the number of unknowns equals the number of equations, they can be solved. If we look at equation 2 only has one unknown. So let's solve that one first. Okay, so equation 2. 0.866t minus 165 equals 0. I add 165 to both sides, and I have 0.866t equals positive 165. I divide both sides by 0.866, and the magnitude of the tension is 165 divided by 0.866, 190.5 pounds. I just found T. Okay? Now I know T. So I can put T into equation number 1, and I can solve for F and come up with the other unknown I'm looking for. Okay, so now let's go to equation number 1, which I know is 0.5 times T. Well, T is 190.5 minus F is equal to 0. Okay, I'm going to add F to both sides, and I wind up with F is equal to 0.5 times 190.5 here, and I have 93.5 pounds according to my calculator. So that's one way to solve two equations and two unknowns. This way, I think, relies upon substitution. If you recall, you can do this with graphing, although this one will be a little bit more difficult with graphing. You can also do this with addition. That also works, but again, this one might be a little bit more difficult with addition. I just saw the fact that equation 2 has just one unknown, And so quickly finding that unknown was easy, and then I could substitute into equation 1 and use that to find the other unknown. So we found our two magnitudes, and that's what we were being asked to find. So let's write it down. Tension T in the rope is 190.5 pounds. Force F with which the climber pushes against the cliff, or vice versa, the cliff pushes against the climber. Either way, it's a horizontal force. Pushes against the cliff is 93.5 pounds. So we're done. A lot here. Okay, that one had a lot going on here, but do notice we've been doing a lot of the same things. When they're not at right angles, we've been making a table to get us to our two resultant components. In this case, we had to make use of the fact what equilibrium means. We've continued to make use of the Pythagorean Theorem, the inverse tangent function, etc. Problem solving is not easy. I can't do every possible situation. You just have to kind of work with it, mess with it some, try, go back to the drawing board perhaps, but that's kind of how it goes.